Welcome to Leveraging Hybrid Cloud HPC with Multi-Tier Reactive Programming. I am Daniel Sokolowski, and this is joint work with JP Lehr and Christian Bischoff, as well from Technical University of Darmstadt, and Guido Salvaneschi from the University of St. Gallen. The advent of cloud computing made huge amounts of resources available. In the cloud, these resources can be booked flexibly and on demand, allowing to scale applications dynamically whenever needed. It would be great to use the cloud also for HPC applications. Especially existing HPC applications could benefit from dynamically adding cloud resources on demand to the already used on-premise resources. However, today's HPC applications are developed for on-premise clusters. Accordingly, current HPC applications rely on static setups. This means they cannot scale dynamically and they typically don't tolerate failure. Moreover, they rather support homogeneous resources, making it hard to adapt to new or different kinds of hardware. Adding cloud resources dynamically to such applications is impossible. But what are the technology requirements to develop scalable, fault-tolerant HPC applications that can be executed hybrid, on-premise and in the cloud? What do we need for high cloud HPC development? First, high cloud HPC development should support multiple program, multiple data, or short MPMD. With MPMD, it is easier than with common SPMD to implement flexible, component-level scalable applications. Second, to avoid waiting times, work packaging should be task-based and the control flow and communication should be asynchronous. Third, the technology has to support various setups and adaptation at runtime to allow fault tolerance and scalability. Currently used technologies like MPI and OpenP have features for these requirements. However, their use is prohibitively complex, while they are practically not used. We therefore propose to use multi-tier reactive programming. Multi-tier programming allows to develop different components of a distributed system jointly in a simple compilation unit. Reactive programming simplifies the implementation of encapsulated, composable code and visualizes the data flow clearly. Combining both in multi-tier reactive programming simplifies distributed application development in the MPMD style. Moreover, it provides language abstractions for asynchronous control flow and communication. And lastly, the raised level of abstraction and the state-of-the-art type system make it easy to implement applications that are adaptable, scalable, and fault-tolerant. While this sounds good, recent multi-tier reactive programming languages not only raise the level of abstraction, they are also based on languages with automated memory management and virtualization. Specifically, they run on the JVM. You might ask, doesn't that introduce a performance nightmare? Perhaps, but that doesn't have to be. We want to use multi-tier reactive programming only to orchestrate optimized kernels. These kernels shall still be written in fast and hand-optimized C or C++. We then implement the high-level application logic and all inter-process communication in the multi-tier programming language and call the kernels through the Java Native Interface, or short JNI. This combines the best of two worlds: native performance with language abstractions that simplify the implementation of adaptable, scalable, and fault-tolerant applications. To leverage high cloud HPC using multi-tier reactive programming, we apply 3 steps to existing HPC applications. Let me explain them. In the first phase, kernel identification and extraction, we take the existing application and apply PIRA to identify the kernels. PIRA, or longer, the Performance Instrumentation Refinement Automation Framework, helps to find computationally intensive parts of the application. It runs iteratively in a build, run, analyze cycle. First, it builds the program and instruments it using SCORP and LLVM-based instrumentation. It then runs the instrumented application with user-defined configurations and records profiling information. In the third stage, PIRA analyzes the execution using a whole program call graph to find a better low-overhead instrumentation for the next build. Through this analysis, we find the computationally intensive parts of the application which are the potential kernels. After we identified the kernels, we extract them as C++ or C functions, which are then callable via JNI. Furthermore, we obtain the application topology through the analysis of the PIRA call graph and the application code. In the second phase, we take the kernels and the application topology and use them to implement the multi-tier reactive application. We identified Scala Loki as suitable, which I will now introduce briefly. Scala Loki is a multi-tier reactive programming language embedded into Scala. It enables us to implement MPMD programs in a single compilation unit. This allows us to benefit from all the well-known type safety features across the distributed code. The Scala Loki compiler then splits the code into separate executables and inserts required communication code. You might wonder, doesn't that mix up things that should be separated? No, it doesn't, because the splitting is explicitly controlled by the developer. The developer explicitly defines the architecture of the MPMD program. He defines peer types for each component and ties for connections between them. In this example, a single manager component, aka peer, is connected to multiple workers. Every values and methods type is then augmented with the peer it is placed on. Here, the secret string is on the manager, and every worker has a work method. Also, all communication between different peers is explicit in the code. For instance, the manager invokes work on all workers as remote procedure call, and the workers access the secret from the manager using asLocal. To distinguish between local and remote invocation has also the advantage that potentially expensive network communication is visible to the developer. Of course, the Scala Loki compiler checks all placement type annotations and communication for correctness based on the expressive type system. Faulty programs are directly rejected at compile time. Apart from RPC-like communication, Scala Loki also features reactive signals and event streams. These abstractions are designed to describe behavior based on change and make it easy to implement flexible mechanisms. Also, the automated asynchronous change propagation is ideal for scalability and fault tolerance in high cloud HPC applications. For high cloud HPC applications, we wrap each kernel in a separate Scala Loki peer. The high-level application logic and all inter-process communication is then implemented, having scalability and fault tolerance in mind. Scala Loki makes this easy and eventually compiles an executable for each peer. In the last phase, we have to decide the placement of the peer executables. The placement decides on which resource which peer is executed, and it is crucial for performance. In this example, we have 3 different peers working in a pipeline fashion. If we assign the same resources to each peer, the slowest will dominate the speed of the whole system. This causes wasted time at the other peers and has to be avoided. So far, we take placement decisions manually and they are static. However, we currently work on abstractions for automated placement and for dynamic placement. This will allow smarter placement decisions to change the location of a peer during execution. For these placement decisions, we also take the performance profiles obtained through PIRA in the first phase into account. To evaluate our approach, we applied it to an SVP solver code. SVP stands for shortest vector problem, and it is a key algorithm to evaluate the strength of lattice-based quantum-resistant cryptography. As baseline for our work, we chose the sequential implementation of the state-of-the-art P3 enum algorithm proposed recently by Burger and others. We applied PIRA to the code and identified 4 kernels, which we each extracted as C++ function that is invocable via JNI. Then we wrapped each kernel as a Scala Loki peer and implemented the application logic and inter-process communication. The application comprises a single central manager that is connected to a variable number of strands which may join or leave at any time. Each strand is a chain of the other 3 peers. The manager generates tasks individually for each connected strand. After the task is completed, the strand notifies the manager to generate a new task if no solution was found. If a solution was found, the solution is reported to the manager, which then terminates the entire application. Finally, we executed the new application in various setups on an on-premise HPC cluster, in the cloud using AWS Fargate, and in hybrid combination. The execution showed that our Scala Loki reimplementation has similar performance to the baseline code. The slightly reduced runtime we measured is caused by the task generation, which runs in a separate process for our reimplementation, but is included in the strands process for the baseline. We also could show that it is effective to combine on-premise and on-cloud resources in high cloud HPC runs. Finally, the execution confirmed that our reimplementation can handle dynamically joining and leaving of parts of the application. This applies to intended scaling as well as to sudden failures. To sum up, we identified 3 requirements for high cloud HPC application development. We found out that multi-tier reactive programming fulfills them and suggest to use it to orchestrate native kernels. Then, we proposed a 3-steps approach to make HPC applications ready for high cloud HPC executions. We first identify the kernels using Pira and extract them as C or C++ functions. Then we orchestrate these kernels using the Scala Loki multi-tier reactive programming language. Lastly, we decide where to run which part of the application. We applied this approach to our SVP solver code and evaluated it to be effective. More details about our work you can find in our paper. With this, we are at the end of my talk. Thank you very much, and I'll be happy to take questions now.